all are going to really learn about inverse functions before, but you guys are going to be able to learn how to find the inverse of a function. Section 2.2. Okay? So, what is an inverse? What is an inverse? An inverse function is a set of ordered pairs, that sounds familiar, right? Obtained by the exchange of each ordered pair. An inverse function is a set of ordered pairs obtained by the exchange of the ordered pairs. Now that's like official textbook definition of an inverse function. With Anderson's definition of an inverse function, you just switch your x and y coordinates. Okay? It's literally all you're doing when you're finding an inverse function. You're switching the x and y coordinates to find the points that are on the inverse. Okay? An inverse is a right. An inverse is a graph. Okay, it's a type of graph. So just like with any graph, it has points. Okay, it has points. And then you just go from there. Okay, it's a set of ordered pairs, just like a relation was. Okay, so for example, I have this relation, which is 1, 2, 4, -2, and 3, 2. Good time to review unit 1. Is this a function?
Yes.
Yes. What made something a function? That the x's don't repeat and they don't have a 1, a 4, and a 3. So yes, this is a function. What is the inverse? The inverse is when you take the x's and the y's and you literally switch the places. So x becomes y, y becomes x. So the inverse is going to be 2, 1, -2, 4, and then 2, 3. You literally are just taking the y coordinates and switching them with the x coordinates. Is the inverse a function? No. How do you know? X values repeat. More specifically, the 2. Okay? And it's as simple as that. Okay? It's as simple as that. You have the point 1, 2, 4, -2, and 3, 2. So when you flip them, you end up getting 2, 1, -2, 4, and 2, 3. Okay? And as you see, the same x value with the rest. You guys go ahead and do this one. Some of you are already done with it. Try to stay with me though. Do this one. Alexis, is this a function? Say again.
Yes.
Yes, it is. Okay? It is a function. What is the inverse? Thomas, what's the inverse? 4, -2, -4, 3, -5, -8. Beautiful. So looking at the inverse, Sam, is the inverse a function? Samantha? Yes. It is a function. And how do we know, Jose? How do we know? No repeating x values. No repeating x values. Easy enough, yes? That's what an inverse is. Okay? That is what an inverse is. Now, one thing that I will mention, okay? You cannot have an inverse if your graph or your points, whatever, is not a function. Okay? You cannot have an inverse if you do not have a function. Okay? Now, graphing inverses. Okay? Every function and its inverse are symmetrical. or the reflections of one another across the line y equals x. Every function in its inverse are symmetrical. In other words, the reflection over a line, and that line is y equals x. Okay? It's literally a line with a slope of 1, a y-intercept of 0. Okay? And literally, when you are graphing, if you ever have to graph a function, okay, find out what the points are on the original graph. Okay, what's this top point up here? Negative 5, 4. Okay, what's the next point? Negative 3, 1. The next one? 1, negative 1, and 3, negative 4. Okay, when you switch those points and you plot them, they will be symmetric. They will basically be like a reflection over this purple line that you see here. Okay, over this purple line that you see here. So when I flip negative 5, 4, what do I get? 4, negative 5, which is about here. Kind of hard to see on mine. I think y'all has lines, doesn't it? Oh, it doesn't? Okay, good. I need to go down. Right. When I flip negative 3, 1, what do I get? 1, negative 3. When I flip 1, negative 1, negative 1, 1. And when I flip 3, negative 4, I get negative 4, 3. And then I connect these points. Okay? This is a reflection. So if I wanted to fold my paper, basically this black part that's right up here would lie right on top of the orange part on the other side, which it does. Which it does. So, is there a way to tell if an inverse is a function? Yes. Okay? First off, you have the vertical line test. Okay? This will let you know if the original is a function. I think we talked about this when we talked about functions in Unit 1. Okay? But there is a horizontal line test. The horizontal line test tells you if the inverse is a function. Okay? So, just as before, if you have some type of function, okay, let's say you have a parabola. If it passes the vertical line test, meaning that you can draw a vertical line and it hits the graph only at one point, then we have a function, like it does here. You see that? So this one is a function. The horizontal line test will tell us if the inverse is a function. And as you can see, when I draw a horizontal line, it hits in two places. So then off gate, we know that the inverse is not going to be a function of a quadratic.
What would the inverse of a quadratic look like?
The inverse of a quadratic, well, when you reflect it over the line y equals x, it actually causes it to turn on its side. And hence, you know, basically when you do the inverse, you can go back to the regular vertical line test, and that's not a function. Okay. Now, if a function, and this is something that I need you to add in, this is a note, okay? If a function passes the vertical and horizontal line test, it is said to be one-to-one. Okay? One-to-one is a math saying. So if you ever get a question, is this function one-to-one? That means it passes the horizontal and vertical line test. So for example, that quadratic, is it one-to-one? Was it one-to-one? No, it did not pass the horizontal line test, and it has to pass both. Okay? A one-to-one will be, so like, yes, like this one here, the one that was in the black, this will be an example of a one-to-one function. Okay? The one that was in the black. Because it passes not only the vertical line test, but it also passes the horizontal line test. So this would have been an example of a one-to-one function. Yeah. So let's look at this graph. Is this graph a function, yes or no? Yes, it is. Is the inverse a function? Is the function one-to-one? No, it has to pass both the horizontal and vertical line test. And if it doesn't pass the horizontal, it means it's not a function, hence why it's not one-to-one. Questions on the graph when it comes to graphing inverses. Remember, you take your points, you switch x and y, plot them, and you have your graph. Now, inverse of functions, when you're doing it algebraically, there are 3 steps. Because sometimes you'll be given the equation of a function and you have to find the inverse. This is really where the math comes in. 3 steps. You replace f of x with y and switch x and y. Then you solve for y like you would any equation. Replacing y with f to the negative 1 of x. This is inverse notation. This is inverse notation. And last but not least, of course, state your restrictions on your domain. Here we go. Now, let's find the inverse of f of x equals 2x minus 4. Step 1, it says to replace f of x with y. So I'm going to replace this with y. And then switch x and y. So that literally means where it originally was an x, I write y. And where there was a y, I write x. Now, if you want to go ahead and go from the original problem to that line we have right now, that's fine. You can do that, okay? That's fine. You can do that. You don't have to show that step of switching f of x to y and then switch x and y because it's about the switch that's really important. Now, step 2 says to do what?
Solve for y.
Solve for y. So to solve for y, I'm going to get it by itself. So what do I need to do? Add 4 to both sides. This turns into an x plus 4 equals 2y. And then do what?
Divide by 2.
And I divide everything by 2. Okay? So this turns into 1 over 2x, because there's nothing but a 1 beside that x. And what's 4 divided by 2? 2. Equals y. But then a part of step 2, it also says to do what? It says replace it with f to the negative 1 of x, because that is proper inverse notation. That negative 1 indicates we're talking about the inverse and not the original function. Notice the difference? So 1/2 x plus 2 is my inverse. So far, so good? Yep, let's get to that. What is the domain? It is all real numbers. Even though you do have a fraction, only the 2 is in the denominator. It's not like a 2x or, like another expression in the denominator. So it has none of the restrictions, so this is all real numbers. Or you can write negative infinity to infinity. It's up to you. Does everybody know what 2x minus 4 looks like? Like if you were to graph it, what it looks like? It has a y-intercept, negative 4, and it looks like a line, right? It looks like a line. This is what 2x minus 4 looks like. Is it a function? Is it 1-to-1?
Yes.
It is. And its domain is what? What's the domain of this line? What's the range of this? Stuff. Very good. Okay? I think I throw that in there for the review. Let's look at this one. We're going to find the inverse of f of x equals 5 over 2 minus x. Now, the hardest that this can get is dependent on the original function. Okay? This one is, I wouldn't say it's something that's very, very hard, but you just got to be careful. Okay? First step, you replace f of x with y. And then what do I do from here? I have to switch x and y. And then I need to solve for y. Okay? Now, to solve for y, I can't multiply by 5 on both sides because that's in my numerator. But I can multiply by the denominator y minus 2 to get the y out of the denominator. Okay? So that leaves me with 5 on the right-hand side, and then on the left-hand side, I'm multiplying x by y minus 2. Now I can do this one of two ways. I can divide by x to get rid of that x. If you want to distribute, you can do that too, okay? Either or. Me personally, I probably would divide by x because when it comes to me having to find the domain later, it's going to be a lot simpler. So I divide by x because I'm trying to get y by itself. And now the last thing I need to do is add 2. So I have 5 over x plus 2. And this technically would equal y, but because I'm at my last step, I'm going to replace y with f to the negative 1 of x. And this is my inverse. So anytime y is in the denominator, multiply by both sides to get it out of the denominator. Okay? And because we do have a variable in our denominator, and we know our variables cannot equal 0, our domain is going to be x cannot equal 0. And of course, with all the goods. Remember, anytime we have a denominator, we always set the denominator equal to 0. And since I don't have to solve any math, that's it. Questions? Let's look at the last one. I have to find the inverse of f of x equals x minus 1, that quantity squared, plus 2. See, some of you guys are already working. You want to try this one on your own? You say you need help? No? Okay. So I need to replace f of x with y. Once I replace f of x with y, I need to do what? Swap, switch x and y. And now let's solve for y. I subtract 2. Remember, I'm trying to get y by itself. And when I do this, to get rid of the square, I do have to square root both sides to cancel out that square. That leaves me with y minus 1 on the right and the square root of x minus 2 on the left. Now, normally when you take the square root in an equation, you get plus or minus. But this is the thing. Because this is a square power, that means it's a quadratic, which means is that its inverse is not going to be a function, okay? But if we only take the positive part of this inverse when we actually finish it out, then, like I explained to you when Jalen asked what does the inverse look like, it looks like this. This is not a function. But right here at this point, this top part is the positive part of that radical, and this part is the negative part of the radical. But if I don't include the negative part, isn't this a function? So I don't have to put a plus or minus here. I don't want to put a plus or minus here, because then it won't be a function. I want it to be a function. See what I'm saying? Last step. So I have the square root of x minus 1, x minus 2, plus 1. And technically that would equal y, but I need to switch it to the f to the negative 1. And that is my inverse. Do I have one of the restrictions? Sure do. I have the radical 1. And whatever's underneath the radical has to be greater than or equal to 0. So when I solve, x is going to be greater than or equal to 2. And there is my domain. Questions? Few things. Well, a few things. Because the inverse is the swapping of x and y, literally everything is swapped on the inverse. Okay? So, going back to that very first example that we did by hand, I asked you to tell me what the domain and range was for this function. And you might not be able to see it on this one, but we'll do it for the other ones. Okay? The domain and range on the original function is swapped for the domain and range on the inverse. So in other words, the domain of the original is the range of the inverse. And the range of the original is the domain of the inverse. Okay? This one's kind of hard to see because you know both were negative infinity to infinity. Okay? But let's look at this one. I won't do that one because you haven't learned it and I feel like it's going to be too much to try to get to you. Okay? In the blue over here, I drew what the function looked like. It was a quadratic. Okay? And if I add in the x and y axes, okay, so this is x, this is y, okay? It has a vertex at positive 2. The domain of this function would be what? Negative infinity to infinity. But what would the range of this graph be if the lowest point is at positive 2? 2 to infinity. And can't 2 to infinity be written as x is greater than or equal to 2?
Yes.
The range of the original is the domain of the inverse. The range of the original is the domain of the inverse, always. Okay? Always, always. Did you write that down somewhere? You should. Important. Okay? Important. So the domain of the original is the range of the inverse. And then the range of the original is the domain of the inverse. All right, we're going to verify inverses, okay? There will be a point where I'm going to give you two functions. I'm going to ask, are they inverses of each other, okay? How you do that is basically by doing the composite of each function, okay? Taking one function and plugging it in for x into the other, seeing if it equals x, and doing it the opposite way. Taking the other function, plugging it in for x, simplifying and see if it equals x. If both ways work, then the two inverses are functions of each other. So if they are indeed inverses, like I said, you do the composite, okay? So in this case, I'm going to do f of g of x, and I'm going to do g of f of x to see if they equal each other. I mean, not equal each other, to see if they equal x. So I'm going to take g, yes, involves fractions, I know. You're going to plug it in for the x in the f function. So this becomes 6 over x plus 4 minus 4. That's what the composite looks like. I literally took g and replaced x with it. But the 4's cancel out. Don't you see they have a positive 4 and a negative 4? So you have 6 over x. Gotta be careful, because that 6 over x is in the denominator. When you have a fraction within a fraction, how do you simplify that? Keep, change, flip. So because you have a fraction within a fraction, you keep the numerator, change the division of multiplication, and then flip your denominator, which is 6 over x. When you flip it, what do you get? And what happened to the 6's? They cancel and you're left with x. So far, so good. Okay? So far, so good. I did f of g of x and I got x. Let's do f of g of f of x. So I'm going to take G and plug F in. I replace the X in G with the F function. So then I have to do the keep, change, flip again with this part. I keep the numerator, change that division to multiplication, and then I flip the denominator. What's going to happen with the 6's? They cancel out. So I'm left with X minus 4 plus 4, which is, okay? So because both propositions equal X, yes, these are inverses. Questions? All right, so again, if these are indeed inverses, f of g of x has to equal x, and g of f of x has to equal x. That's the only way that they're going to be inverses of each other. They both have to work. So if I do f of g of x, that means in f, I'm plugging in g. So I'm replacing x with a square root of x squared minus 10. Like so. What happens when you square a square root? So I'm left with an x squared minus 10 plus 10. 10's cancel each other out, and I'm left with x squared. Is that x?
No.
No. Okay, that is not equal to x. It has to be x. So that means it's over from there. So once you got to this point, you were done. These are not inverses. These are not inverses. Now, some of you guys may do g of f of x first, okay? So I'm going to do it the other way real quick. When I go to plug in, I'll get x squared plus 10 squared minus 10, okay? All of that's underneath the square root. If you notice, when you have a square underneath, you're going to have to FOIL this, which means on top of everything, you're going to have an x to the fourth now. You're going to have so much more than what could ever simplify down to be x, okay? So this is not going to equal x. So these were inverses, period, okay? They both have to equal x. If one of them doesn't work, then it's not going to work. One may work, but the other one may not work. So you always have to check both, okay? And that's how you find inverses. Using the points, remember, you take the points and do what to get the inverse? You swap them. When you're given a graph, how do you know if the inverse is a function? Which one? Horizontal, okay? And then you have your 3 steps when you're doing it algebraically. You replace f of x with y, switch x and y, solve for y, replace it with the proper notation, and then find your domain.